Jain to all. Today I am here to present the video lecture on topic parallel and ladder structure realization of IR filters, and in the lecture series for subject digital signal processing, and this is my first lecture, and I am Dr. Amit, Associate Professor in EC Department of AKGEC. Okay, so let us start with the realization of parallel systems. Okay, so parallel form realization of IR filters. So you know, parallel form structures are nothing but the parallel connection of sub-transfer function which is decomposed using partial fraction expansion. Means you have given a transfer function, and if you want to realize that transfer function using parallel form of realization, then first of all you will decompose the structure, and after decomposition of the structure you will try to represent the structure try to represent the structure or try to represent the transfer function in this form, where you can see here C represents some constant value, and here is HIZ, where I represents from 1 to k. It means H1Z, H2Z up to so n. Okay, depending upon what type of transfer function or depending upon the type of the transfer function, we are having the values of I varying from 1 to k. Okay. So, generally our aim is to represent the transfer function in a combination of first and second order sections. Means whatever transfer function is given to you, we will try to represent it in form of first and second order sections. Beyond second order sections, we will not be able to represent it in parallel form without decomposing it into single and double order sections. Okay. So, the transfer function Hz is expresses sum of first and second order sections. This I have already covered, and the second order section will be of this form, and the first order section will be of this form. Okay. Now, these then we will represent this transfer function in this form, and then each of the first and second order section can be represented by direct form 1 structures or direct form 2 structures. Okay, direct form 1 and direct form 2 structures. Okay, generally we prefer direct form 2 structures because these structures are canonic in nature. You know, canonic realization is the realization in which number of delay elements are equal to the order of the transfer function. So, total number of delays will become less in case of our direct form 2 realization structure as compared to direct form 1 realization structure. So, whenever we will realize a parallel form of realization, then in that case we will choose direct form 2 structure. Okay. Individual sections are connected in parallel to obtain the overall system. Means if the overall system function is Hz, then you will represent your Hz as H1Z plus H2Z plus up to so n. Now, why we should choose this parallel form of realization structure? The main reason for behind this is that whenever you will apply some input, like here you can see, you can write Hz as Yz upon Xz So, now if you will find out the output, then you can see your input is directly applied to all the subsystems simultaneously. Means if you will write it, then it will become Yz equals to Xz times H1Z plus H2Z plus up to so n. So, you can see the input is simultaneously applied to all the subsystems. These we are assuming as subsystems of this system. Okay. So, you can see that input is directly applied to all the subsystems simultaneously. So, it will give us the increase in speed. So, as the filter operation performed in parallel, that is the processing is performed simultaneously, the parallel form structure is used for high speed filtering application. Okay. So, for high speed filtering application, we will choose this parallel form, and how we are getting the high speed? Because the input that we are applying is directly applied to all the subsystems simultaneously. Okay, now we will see one of the problem based on parallel form realization. So, either we have given the transfer function for the system, or we have given the difference equation that will represent your IR system. So if we will see here, this is the question that is given to you, us. Here the system is represented by its difference equation. So you can see the relationship is, question is yn equals to minus 13 by 12 yn minus 1 minus 9 by 24 yn minus 2 minus 1 by 24 yn minus 3 plus xn plus 4 xn minus 1 plus 3 xn minus 2. So what we will do? We will first take the Z transform on both sides of the equation. So yn, Z transform of yn will become yz, and Z transform of y of n minus 1, if you are having a signal yn minus 1 and you will take its Z transform, then we will simply get Z to the power minus 1 yz. So we will get minus 13 by 12 Z to the power minus 1 yz. Similarly, Z transform of yn minus 2 is Z to the power minus 2 yz. Similarly, for yn minus 3 it will become Z to the power minus 3 yz. Then x of n minus will become Z to the power minus 1 xz. Xn minus 2 will become Z to the power minus 2 xz. And then we will solve it. So by solving this, we are having the value of yz upon xz, which is nothing but our system function hz, and that hz can be represented in this form. Okay. So now either we have given this form directly or we have given this form. We will first obtain its transfer function, and from here we can see that our transfer function, you can see here in the numerator the maximum power of Z to the power minus 1 is 2 and in denominator it is 3. So we have to split this hz in such a manner so that we will get first and second order sections. So here we have represented it. Now if you will factorize it, okay, if you will factorize it, so you will find after factorization you are having this term hz equals to 1 plus Z to the power minus 1 times 1 plus 3 Z to the power minus 1 upon, you can see the denominator part. Now we will represent it in form of, because you can see here there are 3 terms. So we will represent h1z, h2z and h3z with the help of partial fraction. Okay. So you know the partial fraction in this case is a upon 1 plus 1 by 2 Z to the power minus 1 plus b upon 1 plus 1 by 3 Z to the power minus 1 plus c upon 1 plus 1 by 4 Z to the power minus 1. So when we will calculate the coefficient values, we can simply find out the coefficient values by putting the value of Z to the power minus 1 equals to minus 2 in this equation, and similarly for rest of the equations. So we are having the coefficient values as a equals to 30, minus 128 and 99. Then we will put these values here. So we are having hz equals to these 3 terms. So we are assuming that, let us say this is h1z, this is h2z and this is, let us say, h3z, h1z, h2z and h3z. Now we will realize these subsystems to obtain the parallel form realization structure. Okay. So here you can see the structure is made, already made. I am redrawing this structure here only for better understanding. Okay. So you know your terms are this. So what we will do? We will start here with the input. Okay. Now for each of the subsystem, I will choose direct form 2 realization structure. Okay. So for direct form 2, first of all I am drawing h1z. So this is 1 upon, so you will draw direct form 2 realization structure. It is minus 1 by 2. Here adder will be placed and this is the output. Similarly, if you will see here, the value will become minus 128 and again adder will be placed over here and it will become, because plus sign is here, so coefficient value is minus 1 by 2 here. Similarly, coefficient value is minus 1 by 3 here, and if you will draw it here, you are having the value 99 over here, then adder comes over here, and the value of this coefficient will become minus 1 by 4. Now you can add these all three. You can also choose 2 adders, or you can make it by 1 only. So this is how we are obtaining the direct form realization structure. Okay. You can see the same structure is over here. Now come to the another type of structure which is called as ladder structures. So first of all, why should we choose this ladder structures? So filter realized using ladder structures have desirable coefficient sensitivity properties. So if we will do some small changes in the filter parameters, it will not affect the performance of the filter. Means what happened due to some changes in parameters, due to say some changes in the atmosphere, what happened, the parameter values may get changed, and if the parameter values get changed, then the system performance may get affected, or the system frequency response may get changed. Okay. So we should choose a structure which is less sensitive to change in parameter variation. So this is the beauty of this ladder structure, that these structures are less affected by change in parameter variations. So whenever you are having a ladder structures are generally represented by this type of transfer function. You can see the maximum power of n may be anything, but you can see that here in numerator and denominator both is having the power, same power. Okay. So for making the ladder structure from this given transfer function, first of all we have to represent this transfer function in its continued fraction expansion form. Continued fraction expansion form. So this continued fraction expansion form you can easily obtain by dividing numerator by denominator also, but that is not the you can say very good approach. Another approach is like we can find out the coefficient values with the help of Routh criterion. Okay. So I will discuss here problems with the help of Routh-Hurwitz criterion only. Okay. So when you will do the continued fraction expansion of Hz, you are having this type of form: alpha naught plus 1 upon beta 1 z to the power minus 1 plus 1 upon alpha 1 plus 1 upon beta 2 z to the power minus 1 plus up to so on 1 upon, this is 1 upon alpha n. Okay. So so this is the Routh array that I have made for this general transfer function. Initially higher order powers will be there, and then subsequently we will get up to z to the power 0, and here are the coefficient values. You can see in an minus 1, a1, a naught here, like, and denominator coefficients are in the second row, and then cn minus 1 can be calculated by multiplying bn with an minus 1 minus an into bn minus 1 upon bn. So this is the some approach by which we will try to obtain this. We will obtain the first column of the Routh array. So once first column of Routh array will be obtained, then we can easily find out the values of alpha naught, beta 1, alpha 1, beta 2 and up to so on. Okay. So in the numerical part I will discuss how we are getting this Routh array coefficient values. Okay. So then ladder structure parameters can you calculate like alpha naught equals to an upon bn, beta 1 is bn upon cn minus 1, and similarly. Okay. Now we will also see how the structure will be made. Okay. So now if you will see the first term, it will become alpha naught. So the overall transfer function Hz can be represented by yz equals to Hz times xz, where Hz can be represented in this continued fraction expansion form. So once we will obtain the continued fraction expansion form, then how we will draw the structure? We are seeing only this thing. Okay. So alpha naught plus 1 upon beta 1 z to the power minus 1 plus, we will take this whole term as R1z. Okay. So if we are taking this whole term as R1z, so it will become alpha naught plus 1 upon beta 1 z to the power minus 1 plus 1 upon R1z multiply by xz. Then we will solve it. So alpha naught xz and another term is 1 upon beta 1 z to the power minus 1 plus 1 upon r1z times xz, which is nothing but h1z. So, we have assumed that h1z is this whole term. Okay. Now, if we have to simply draw the structure for this equation 1, then it is you can draw it using this because plus sign is there. So, there is a parallel structure over there. So, if input is xz, then multiply by alpha naught, we will get yz, and in summation we are having h1z xz. So, this is h1z and xz input is here. So, we are getting the output y1z. Okay. So, this is the basic structure or realization structure from equation 1. Now, this r1z we have taken as alpha 1 plus 1 upon beta 1 z to the power beta 2 z to the power minus 1 plus up to so on. So, now after this we will try to realize this equation number A. Okay. So, now from here, from this figure 1, you can see here this h1z is having input xz and output y1z. So, h1z is y1z upon xz, and this is equal to 1 upon beta 1 z to the power minus 1 plus 1 upon r1z. So, this is how we are getting this equation number 2. Now, we will cross multiplying it, and after cross multiplying it, we are having y1z times beta 1 z to the power minus 1 plus 1 upon r1z equal to xz. Okay. And then we are solving it. So, we are having the value of y1z equals to r1z times xz minus beta 1 z to the power minus 1 y1z. So, with this we are assuming at x1z. So, this we have written as x1z. So, now we will only draw this structure, means for this part xz is the input, y1z is the output. So, now we will draw this structure. So, you can see y1z is the output, and this y1z beta 1 z to the power minus 1 y1z is nothing but it will come in feedback path. Okay. So, this is the structure, this is the structure of, you can say, where x1z is the input and y1z is the output. Okay. So, for the realization of equation 4, we can draw this structure, and with the help of equation 2 and equation 3. Okay. So, with the help of these 3 equations, we will draw this structure. Okay. Now, you can see here in this structure, the input is xz and output is y1z. So, you can see here structure is in this structure xz is the input and y1z is the output. Okay. So, now in this figure 1, this h1z can be replaced by this complete structure, because h1z is nothing but having input xz and output y1z, and similar is the case here. So, what we will do? We will combine these 2 structures. So, when we will combine these 2 structures, we are having this structure, which is known as figure 3. Okay. Now, again what we will do? Now what is the next step? Again what we will do? We will try to represent r1z in form of alpha something plus 1 upon r2z like this. So, this r1z can be represented as y1z upon x1z, which will be equal to alpha 1 plus 1 upon beta 2 z to the power minus 1 plus 1 upon r2z. Okay. It means now if we will see only this part, so between x1z is the input and y1z is the output, we can draw this structure like this. Okay. In terms of r2z, means r1z in terms of r2z, and similarly r2z in terms of r3z, and up to so on. So, ultimately what happened? We are having this type of structure, and this structure will be continued until when all the coefficient values are not covered. Okay. So, we can see the structure of ladder like this. Here you can see the adders are putted alternate like this. Signal flow is traversing like in this direction, top to bottom and then bottom to top. Input is xz, output is yz. So, this is the ladder structure realization of IR system, and this is the final structure. Okay. Now, we see one problem, that how we have made this structure and how we have calculated the coefficient values. So, this is the question. 2 plus 8z to the power minus 1 plus 6z to the power minus 2 upon 1 plus 8z to the power minus 1 plus 12z to the power minus 2. So first of all we will write it in like this, so that maximum z power negative power will be on left hand side. Then we can simply write these coefficient values 6, 8 to 12, 8, 1. Here z to the power minus 2 term is there because the maximum power is z to the power minus 2. Now this term, how we will calculate this term? You can see 12 into 8 minus 6 into 8 upon 12. So we are getting the value 4. Now how we will get this 3 by 2? 12 into 2 minus 6 into 1 upon 12. So we are having the value, if you will solve it, you will get the value 4, and if you will solve it, you will get the value 3 by 2. So we are having this row values. Then again this value, how we will get this value? 4 into 8 minus 12 into 3 by 2 upon 4. So we are having this value 7 by 2, and similarly we will obtain all the coefficient values in the first column of Routh array, So once our Routh array is completed, then we are interested only in this first column values. Okay. So now how we will obtain the coefficient values? Alpha naught is this divided by this, so 1 by 2, 12. So alpha naught is 6 divided by 12, that will become 1 by 2. Then next value is beta 1. Beta 1 is 12 divided by 4, that is equal to 3. Then alpha 1, 4 divided by 7 by 2, it means it is 8 by 7. Then beta 2 is so it will become 49 by 5, and then alpha 2, this is 5 by 14. So now we are having these coefficient values, we can directly put the coefficient values here in this equation. So we are having the value Hz, which is in this form, which is nothing but the continued fraction expansion form for Hz, Okay. Once we are having this continued fraction expansion form of Hz, we can directly draw the structure. Like this alpha naught coefficient comes as a single multiplier here. Here is the input, here is the output, and this beta 1 sign, you can see the structure here, we are having the negative value of beta. So that's why minus 3 is put over here, then z to the power minus 1, and in the direction of signal flow we will put the adder. Like here signal is transmitted from here to here, signal here to here, that's why adder is here. Again this is alpha 1, which is 8 by 7, we will put it over here, then 49 by 5 beta 2, so it is here, and then it is 5 by 14. Okay. So this is how we are getting this structure. Let us suppose this equation is of third order, then what happened? 2 more rows will be added, and we are having 2 extra coefficients, that is beta 3 and alpha 3, and so that your structure will be like expanding. Okay. So this is how we will draw the ladder structure. Now we can see one more problem based on this ladder structure. Here again you have to realize the ladder structure. Okay, but here in this case you can see the transfer function that is given to us is in positive powers of z, and the structure that we have made is dependent or is made using the negative powers of z. So what we will do? We will first convert these positive powers of z in negative powers of z. How we will do it? We will simply multiply by z to the power 2, z square in numerator and denominator, so that we are having this form. So you can see again the question will remain same. So now we will write the values like coefficient of z to the power minus 2 is the highest. So we are writing it z to the power minus 2 like 4, 5, 3, 4, 5, 3. The next is 8, 6, 1, 8, 6, 1. Now how we are getting this value? Simply 8 into 5 minus 4 into 6. Okay, and how we are getting this value? 8 into 3 minus 4 into 1 divided by 8. Okay. So similarly, we are completing this Routh array. Again, this value can be calculated with the help of this, multiply by this, minus this, into this, divided by this, and similarly this value, this value. So once we are having these values, alpha naught will become 4 by 8, which is 1 by 2. Then beta 1 is 8 by 2, that is 4. Alpha 1 is 2 by minus 4, that is minus 1 by 2. And it is minus 4 by 3, and last is 3. So once we have calculated this, we can draw the structure. Okay, so you can see here alpha naught is 1 by 2 comes over here. Then beta 1 is 4, so sign is minus 4, z to the power minus 1, and then alpha 1 is minus 1 by 2, so you can see here it is minus 1 by 2, and here it is minus 4 by 3, so you can see the coefficient value will become 4 by 3, and lastly 3. So this is the structure for the transfer function 3z square plus 5z plus 4 upon z square plus 6z plus 8. Okay. So this is in this video lecture I have covered basically the parallel realization structure and ladder structure realization. Okay, and basically these are the references that I have taken for making this PPT. Thank you so much.